Hello guys, greetings from Los Angeles. Good morning, good afternoon, and good evening. My name is Cheng. I'm a PhD student from UCLA. Let me begin this video by a simple question. Have you ever complained that your FPGA design takes forever to compile? If so, you are at the right place. Welcome to Project RapidStream. This project is a collaboration between UCLA, Xilinx, Ghent University, and Cornell University. It is my honor to represent the team in this video. Nowadays, both the capacity of the FPGA devices and the size of our designs are increasing dramatically. The result is a surge in compile time. It is not uncommon that a large design may take tens of hours to compile into hardware bitstream. Why is it so slow? We profiled the CPU utilization in the compilation process and found that, on average, only about 2 CPU cores are active.
In this figure, the horizontal axis is the time and the vertical axis is the number of cores active.
From another perspective, we measure the total compile time as we increase the number of threads. It turns out that the yield is negligible beyond using 4 to 6 threads.
This figure shows that using one thread will take more than 20 hours. Using 4 threads reduces the compile time to around 15 hours, but using more threads can hardly get us more speed up.
Worse, and seemingly endless compile process does not mean a high timing quality of the output. As we scale up the design size, the final frequency continues to drop. Note that the existing CAD flows are all developed for RTL designs. The tool must maintain the exact behavior as the cycle-accurate input RTL. Due to the inherent sequential nature of many of the CAD algorithms, it is hard to parallelize this process. However, new opportunities may arise if we try to tackle this issue at the HLS level. Compared to an RTL design, an HLS flow starts with untimed C++, and the HLS scheduler has the flexibility to add more pipelining if necessary. Can we utilize this flexibility to pipelining to speed up the downstream physical implementation? Previous works on this direction rely on a pre-built overlay. They organize the FPGA fabric as a set of disjoint islands connected by some pre-implemented structures, such as network on chip or pre-routed wires. Then they can try to split the design to map to the islands. Since they are pre-built structures to completely isolate each island, all islands can be implemented in parallel. However, while the pre-built structures make it possible for a split compilation, they severely limit the quality of the design. An input design may not match the structures well, resulting in area overhead, performance drop, low timing quality, as well as reliance on manual help. To address this issue, we present RapidStream, a new methodology to enable split compilation of HLS dataflow designs. Compared to previous works, RapidStream completely gets rid of the pre-built structures. It is a fully automated flow from C++ to a high-frequency physical implementation. Compared to commercial tools, RapidStream achieves 5 to 7x initial speedup with up to 1.3 times frequency improvement. With our ongoing efforts, we prototype up to 10 times end-to-end speedup. We have fully open-sourced RapidStream on GitHub for the community. Here's an overview of the RapidStream. We start with an HLS dataflow design. Phase 1 automatically partitions the HLS design and pipelines the connections between partitions. Phase 2 implements each partition in parallel without relying on any pre-built structures for isolation purpose. Finally, Phase 3 stitches the partial output together into the final physical implementation. While the divide and conquer idea may seem intuitive, it is challenging to get speed up and high frequency at the same time. There are dozens of steps and several major technical challenges that we must address. Let's start with a more in-depth introduction of Phase 1. The first key idea is that when we partition the design, we will insert an anchor register for every inter-partition net. To do that, we convert a normal FIFO to one such that the full signal is asserted in advance. Then we can safely pipeline the handshake interface of the almost full FIFO. Next, we organize the FPGA fabric as two types of regions: large disjoint islands and thin anchor regions between the islands. Based on this setting, Phase 1 partitions the logical design to match the physical device. For more technical details of the partition process, please refer to our paper. Next, in Phase 2, we aim to parallelize the placement and routing steps. Although the anchor registers provide crucial isolation of the cross-island timing path, anchors and islands are still interdependent, like a chicken and egg problem. We propose to use an iterative approach to break the dependency. In one iteration, we lock the locations of all anchors and adjust the placement of islands. In this step, each placer process optimizes one island based on the surrounding anchors. In the following iteration, we fix the replacement of all islands all in turn. Then we adjust the anchor locations to best match its adjacent islands. To parallelize this step, each placer process handles a pair of islands and optimizes the anchors in between. Specifically, for iterations that optimize the islands, we resort to the standard placer because of the complexity. Meanwhile, for iterations that optimize the anchor regions, the problem is much easier, and we formulate the situation as a weight matching problem in integer linear programming. The details of this formulation are described in our paper. In practice, we observe that the overall timing quality quickly converges after only about 3 iterations. Next, we present the challenges and solutions in parallel routing. Since all inter-island nets are anchored or pipelined, each router process handles one island and connects it to the surrounding anchors. However, there is one global signal remaining, that is, the clock signal. A naive solution is to first route each island under an estimated clock tree. The problem is that there will be variation in the clock skew if the clock tree changes after stitching. Even tiny clock skew variation can cause hold violations that cannot be fixed by lowering the frequency. To address this issue, we implement a hierarchical clock routing approach to ensure that the clock tree is consistent throughout. We also disable the potential time borrowing optimization on the anchor registers. Our clock management scheme ensures minimum and negligible timing variation after the stitching step. After all islands have been routed, we stitch them together using the RapidWrite framework.
RapidWrite is an open source project that allows users to manipulate the desired checkpoints in a Xilinx Vivado workflow. In our case, we will use RapidWrite to edit the netlist of each island to put them together.
To ensure scalability, the stitch is performed hierarchically. The final step of the flow is to fix potential conflicts in inter-island nets after stitching. As the figure shows, two islands connect to the same anchor registers through shared routing resources. Therefore, it is possible that there are routing conflicts in this shared resource after we stitch two islands together. As a result, we need to invoke the router after stitching to do a final pass of regop and reroute about the inter-island nets. Now let me present the evaluation of our flow. We test on 6 large-scale dataflow designs on the Xilinx U250 FPGA. Results show that we achieve a 5 to 7 times end-to-end speedup with up to 1.3 times frequency improvement.
The left and the right figures shows the frequency and runtime comparison of RapidStream versus Vivado, where the blue bars represent the results of RapidStream. As you can see, RapidStream achieves better frequency while it's significantly faster than Vivado flow.
RapidStream schedules the individual tasks asynchronously. For example, in this figure, we can see that at the 11th minute, there are 9 islands that are still in synthesis, while 23 islands are already in placement. This chart shows the potential timing degradation if we do not apply our clock management scheme. While the absolute value of decrease in the setup or hold slack may not seem much, it will almost always result in hold violation. Our clock management scheme prevents this issue by ensuring that a stable clock skew is maintained before or after the stitching process. Next, we profile the CPU and the memory utilization in the typical RapidStream flow. On average, we are able to keep about 26 cores busy, while a traditional RTL flow does not yield much speedup beyond using 4 to 6 cores. Note that there is a long tail issue with low CPU utilization in the figure. That corresponds to phase 3. Remember that we need to invoke the router again after stitching to resolve the inter-island conflicts. However, existing commercial routers are not designed to handle local partial routing, and therefore has a large runtime overhead. To address this long tail issue, we have ongoing efforts to develop a customized partial router, which is specialized for fixing local conflicts. We built the functionality on top of the open source router RWRoute, and we add timing-driven support and the dynamic bounding box support to the partial routing module. Even with just one thread, our lightweight router is 4 times faster than Vivado for this specific task. With that, RapidStream can achieve 10 times speed up end-to-end. Note that RWRoute currently relies on public timing models. Since they are not open model for hold violation, RWRoute at this stage cannot fully resolve hold violations yet. In our paper, we present additional techniques of using the clock phase shift to eliminate hold violation while sacrificing the frequency a little. When an open hold time model is available, RWRoute could completely get rid of the hold violation and replace Vivado for this step, thus achieve the prototype the 10 times speed up.
Still, even with the long tail issued by Vivado router in phase 3, the whole RapidStream flow still achieves 5 to 7 times speed up in a runtime, and the current result is fully legal with no hold violation.
Now let me summarize the work. To the best of our knowledge, RapidStream is the first automated, parallelized, and high-frequency CAD flow for HLS dataflow designs. It identifies and prototypes up to 10 times speed up compared to a commercial tool, and increase the frequency by up to 1.3 times. If you find this work interesting, please take a look at our GitHub repo and give us a star. Your support is the biggest momentum for our research. Finally, it remains as future work to build a corresponding infrastructure for RapidStream to enable communication between the host and the FPGA. That's all for today's presentation. Thank you for watching.